Okay, good morning, everyone. Sorry for the delay here. I am new to Second Life, and so this is I'm trying to get my screen so that I can see what I'm talking about here. So, welcome to everyone. I'm sitting here at NASA Ames Research Center in just south of San Francisco, California, north of San Jose. I am a education specialist, a STEM K-12 education specialist, do mostly professional development. So at the end of the program, and hopefully I'll remember to do this, at the end of the program, I'd like to get introduced to each of you and just tell me your affiliation, why you're interested in being here, whether you're a teacher or university professor or just an interested person. So we'll do that at the end. Good morning, NASA. Thanks, Vic. Okay, so feel free to ask questions as we go along here. I'll be monitoring the chat box, or Chantel, if you can somehow let me know, or Vic, you can chime in with your voice if you need to and ask me a question. That would be great. I just want to make sure that I get everyone's questions taken care of as we go. So the talk today, let me turn around real quickly, see who we've got. Interesting avatars here. Okay, excellent. So the talk today is entitled, let me get my screen back up here again, is entitled Exploring the Surface of Mars, Searching for Clues of Life, and you see it here on the screen. So here at NASA Ames, astrobiology is a big part of what we study here. This NASA Ames is something called is an astrobiology institute, and so there's a lot of study on exobiology, looking for life on other planets, and especially on Mars. NASA Ames also is the primary center for a mission looking for life on distant planets, the Kepler mission, and hope maybe I could come back and give a talk sometime on the Kepler mission. This is looking at 150,000 stars near the Cygnus constellation, and it's analyzing whether those planets are the right size and the right distance from their star in order to have habitable environments. And actually I'm giving a talk on that subject a little later on today. Okay, so I'm in education professional development, so I work with teachers. There's the Kepler website right there. Thanks, Vic. You can find out more about Kepler at that site. Great. So Chris McKay, a good friend of mine, is an astrobiologist here at NASA Ames. He's been on many documentaries, so he's kind of tall and skinny, always wears a denim shirt and pants. So you may have seen him on public television. Any show about Mars usually has him. Phil Christensen is a professor at Arizona State University, and Rick Varner was a colleague of mine in the program. He's back teaching again, but I was a high school science teacher, and I've been with the NASA 11 years as an education specialist. So we will continue here. Let's see. Okay, next. As I said, this oops, there we go. Browse and next. There we go. Okay. So NASA, of course, stands for the National Aeronautics and Space Administration, and hopefully you're all familiar with NASA. This would be a time when I would ask you if you had visited the NASA site. National Aeronautics and Space Administration. NASA was established in 1958. Who can tell me, you can type this into the box there, who can tell me why it was established in 1958? Is anyone? Sputnik. Very good, Vic. I think you're a ringer out there, Vic, so we're going to have to going to have to keep you quiet because you're going to answer everything. So yeah, Sputnik. And Sputnik was 1957, and that's right. And 1957 is when Sputnik was, and President Eisenhower used Sputnik as a direct reason for starting NASA. He took another national organization called NACA and took those scientists and changed those into space scientists. Okay, very good. So NASA got a lot of scientists from other parts of the world, and probably the most famous one came from Germany after World War II, and he developed the first rockets, some of the first rockets for NASA. Who can tell me who that person is? I'm going to try to keep this interactive so I know that you're not asleep out there, so go ahead and feel free to. Werner von Braun, very good, excellent. Okay, excellent. So again, here's my background, NASA Ames Research Center. I work for Paragon Tech, and there's my email, and I'm going to have my email up at the end. If you're interested in having this PowerPoint, then you can email me, and I'll give you a link. I'll invite you to my Dropbox, and you can have this PowerPoint to use in the classroom. It can't be used commercially, of course, but it can be used in the classroom. So this top picture up here is me, and then I've done lots of things, teacher workshops, working with students down on the lower left side. The center one there, I'm working, I flew on the microgravity plane, the KC-135, and flew in microgravity. And then the right side, I'm working with some students on an asteroid lesson. Horowitz. Yes. Okay. Yes, that's right. Who can tell me back to the beginning of NASA? Who was called basically the father of rocketry here in the United States? Does anyone know that question? And one of the centers, that's right, Robert Goddard. Very good. All right, excellent. Can't fool you guys. Okay, so the big question is about astrobiology, and of course Mars is, did life develop in more than one place in the solar system? We know we have life here, okay? The question is there life other places? Now, who can name other places possibly besides Mars that life possibly could exist here in the solar system? Europa, very good. Okay, any other places? Enceladus, very good. Okay, thank you, Danelle. Leo, Europa is correct. Any other places where life might possibly exist? Any place with liquid water or methane? Very good. One of the moons of Saturn, Titan, has liquid methane. Meteorites, very good. Yes, there was a meteorite, very famous meteorite, which was a Martian meteorite, which scientists analyzed and looked at and said that there may have been a remnant fossil, but it was smaller than a bacteria, so it would be really, really hard to. Okay, what do we know about Ceres regarding life signs? We've got a spacecraft actually on the way to Ceres right now. It's called the Dawn mission. It visited, boy, it's been a long time since I heard. It visited Vesta, which is an asteroid, and now it's going to Ceres, which is a dwarf planet in the asteroid belt. Okay, and so we'll know a lot more about Ceres after the Dawn mission visits Ceres. So these are our two closest neighbors. Of course, all the blue on Earth, the oceans are teeming with life, and life is obviously very common on Earth. we're not sure if Earth has intelligent life yet. That's still a open question. So the other two places we're looking at here, the Moon and Mars. Now, what about the possibility of the Moon having life? What are some of the limiting factors on the Moon that would be difficult to have life? There is water on the Moon. We found water with several satellites and also the Mars Reconnaissance Orbiter and the Moon Reconnaissance Orbiter. No liquid water or methane. Very good. Okay, also no atmosphere, all right? And because the gravity is much less, yes, with no atmosphere, it has a lot of exposure to cosmic rays. Excellent. Okay, good. So the question is, with astrobiology, is there life here in this near neighborhood? Okay. So what are some of the signs that Mars could have life? Who can tell me a few things about Mars? First of all, how does it compare to Earth? If we take Earth and Mars and compare the two. 1/2 the mass, okay? It's 1/2 the diameter. Same amount of land surface, right? Even though it's 1/2 the diameter, same amount of land surface. How about atmosphere? Atmosphere is actually very thin, so it gets a lot more cosmic radiation than it does here. Yeah, lack of a geothermal engine to maintain a magnetosphere. Okay, so it doesn't have a magnetosphere, although it must have possessed a magnetosphere in the past, because there are areas, the older rocks on Mars have magnetic signature. So at some point Mars had a magnetosphere which would have deflected a good bit of the solar radiation. Okay, so the history of Mars, yeah, no tectonic movements, exactly. That's right. But it has to do also with the magnetosphere and how much it would have been protected from radiation. And if the atmosphere is protected from radiation, then it could have harbored a much denser atmosphere, which would have been a warmer planet, as well as a planet that was protected more from the radiation. Okay? Okay, so yes, no, and maybe. So we look at some of the other places, and you folks named all of them. And Mars actually is the one, at least in the common thoughts of scientists, the one that is the least possible to have life. And that's where we are now, because it's the closest. But Europa with the organics, and Enceladus because it's extruding water, ice out into the atmosphere. You can see the picture of it there, where it's actually there are geysers that come off the surface, blowing water ice out into space. Cassini, which is a spacecraft which is at Saturn, has flown through this plume. It has no instrumentation to detect life, but it could detect some of the chemicals, and it did determine that it was water ice, and I believe yeah, it says organics as well as nitrogen. So some of the components that are needed for life are in that water. And then of course Titan with no water, but of course methane, which is organic. So why are we studying Mars? Well, you see the first image, which was the image which was Percival Lowell, and from that we thought that there might be water channels on Mars, that civilizations on the surface actually had canals that went from place to place. So the idea, the one on the right, would have been possibly an ancient Mars, okay? And the ancient Mars would possibly have been warmer, okay? And may have had life and oceans. Now we know now that Mars definitely had oceans from the Mars exploration rover Spirit and Opportunity. They found evidence of salts, salt layers, and also hematite. Okay, So evidence of past water, the atmosphere, obviously CO2 with a little bit of nitrogen, and good possibility of preserving life. So the idea that there might be life on the surface is certainly driving the exploration. So here is some of the timeline of following the existence of water and Mars Odyssey, and before it the Mars orbiter. So European Space Agency in 2003 sent an orbiter, which is still orbiting, and most recent orbiter was the Mars Reconnaissance Orbiter. Now there's an orbiter on the way called the MAVEN mission, and it's going to be looking at the Martian atmosphere and determining what the composition of the Martian atmosphere is precisely, and to be able to determine how that may have changed over time. Okay, and that is scheduled to arrive. I believe it launched. It launched this year, and I think it arrives in 2014. Okay, it's about a 9-month trip. Okay. So obviously, from satellite images, Mars has at least visual evidence that there was water. This is a dendritic braided channel system, which shows that some sort of liquid flowed on the surface and collected into larger liquid flows. Okay, unlikely that that volcanoes would look exactly like this and would have this pattern. So the Mars Reconnaissance Orbiter has really given us some great up-close views of Mars. It has something called the high-rise camera, and you see the detail that you can see the channels and the impact craters. It caught a dust devil trail you see on the lower left side. Spirit and Opportunity benefited. Spirit especially benefited from the dust devils. It was losing power because it was solar powered, and because the solar panels were getting covered up by dust, many dust storms on Mars. And so suddenly one day the power generation went up. The power supply increased rather dramatically, and it was, I think it was like 30%, and all of a sudden it jumped back up to 75%. And what they determined was that a dust devil came through the area, and they were concerned that dust devils would deposit material, but this one actually cleared off material. The wind from the dust devil cleared off material. And then the Barcan Dune. So obviously there's a lot of wind on Mars. I think that's fairly well known. So some other images, the Mars Recorder, the Mars Reconnaissance Orbiter indicated that there must be water or some sort of flowing material. If you look at the upper left-hand corner, those gullies may very well have been caused by water. The apron above that, the darker line above that goes diagonally across the screen, is the edge of a cliff. Okay, so that's an escarpment. And as you go downhill from that, the outwash plain, you can see a typical pattern that looks like water, a carved out flow, and then at the bottom you see alluvial fans, okay, like a delta except on the land. Now on the right, a little bit different, you don't see any alluvial fans at the bottom, and these actually look like raised areas rather than carved out areas. They were a raised area. This is probably and you can see, because it doesn't have an alluvial fan, it's not transporting material. So this wasn't a liquid that flowed. Most likely it was dry ice that formed and then evaporated. Dry ice will form in the wintertime, and then a lot of it will evaporate, making the poles much smaller in the summertime. So there's a huge seasonal variation. Again, feel free to ask questions as we go along. Okay, alrighty. Feel free to ask any questions. So again, more recently, this is the more recent history of exploration, going back to the Mars Odyssey and also the Mars Global Global Orbiter, and MRO. So Curiosity landed in 2012. You see Spirit and Opportunity down at the bottom in Phoenix. Phoenix ended its mission in 2008. So the Maven mission is landing in this year, later on actually in 2014. And then there's a planned European Space Agency NASA collaboration in 2016, and hopefully more rovers as money and politics dictate in the future. Okay. So let's take a little bit closer look at the family of rovers that NASA has. Oh, an article. Okay, very good. Thank you, Vic, on Mars plate tectonics. Sure, Mars has volcanoes, and we still haven't put a seismometer on Mars to determine whether there's Mars quakes, and I think that's really important to get done. But anyway, this is the United States NASA rover family. The first one is the Sojourner from the Pathfinder missions back in the mid-1990s, 96 I think through 97 or 98. And then of course the one on the upper left is the Mars Exploration Rover, Spirit and Opportunity. Two twin rovers. We'll see where those landed, both near the equator, because the top of Spirit and Opportunity are solar panels. Okay, and you see the size difference from Sojourner up to Spirit and Opportunity. Spirit and Opportunity for about 400 pounds, and it's about the size of a golf cart, if you think of a golf cart. And then we switch over to Curiosity, a much bigger vehicle. It's about the size of a Mini Cooper, much larger, and instead of 400 pounds, it was a little over 2,000 pounds. Okay, so a five-fold increase in the weight. And you also don't see any solar panels. Who can tell me what the Curiosity rover is powered by? Yes, it is nuclear. It is powered by a nuclear generator, okay, an RTG, that's right. And that allows it to work both daytime and nighttime, although they don't drive it around very much at night. But it's going to allow a longer life as well. Spirit and Opportunity only had a 90-day warranty. Opportunity is still going after, what, 2004, after about 12 years. Spirit has shut down because it got stuck, and then it had some issues. So it is shut down. Opportunity is still trucking across Mars. Why is there a waterfall sound? I don't know. Maybe I have... Do I have additional sounds on here that I can shut off? I don't know. I can hear the waterfall sound. Okay. All right, very good. Okay, so those are the rover family here. And I clicked next, but let's see. I didn't get next. Here we go, browse, and next. So let's look at the location where these landed. Of course, the Viking missions were back in the 70s, Viking 1 and Viking 2. And Viking 1 and Viking 2 were landers that landed on the surface and took scoops of soil, and they were looking for bacteria. They had a chemical that perchlorate that they mixed in order to react, and it turns out the perchlorate would have killed the bacteria if there was. There was no bacteria, so that set back the Mars exploration by a number of years. So Spirit and Opportunity were next, and Spirit is way over here to the right. It was at Gusev Crater and in an outwash there was what looked like and was agreed upon that a river water had flowed into this crater, and there was a delta inside the crater, and so that's why following the water, that's why Gusev Crater was chosen. Opportunity was chosen because there was an area that had hematite detected from the Mars orbiters. And so hematite formed here on Earth is formed in the presence of water. It has water as a primary portion of its chemical structure, and the hematite that they found here, they wanted to land there to see if that hematite was related to water here on Earth. Okay, and Opportunity, both Opportunity and Spirit found evidence of water. Okay, and Opportunity measured the hematite, and it was the type of hematite, and what's that type now? I can't remember, gosh, it's been so long. Okay, so Curiosity, you can see where Curiosity landed, just kind of northwest of Spirit. Okay, and let's look at the next slide to see why it landed where it did. Okay, for some reason I get my slides, and okay, there we go. So this is a map of Mars that is color-coded by altitude, and you see the largest volcano, which I don't have my pointer, so the largest volcano in the upper left, Olympus Mons, is up on the left there, and that is called the Tharus Rise, where the red area and the brown area is up on the upper left, and then the blue, the dark blue, is the Helena Planaris, which is a huge crater impact with much more smaller crater impacts overriding it. Okay, the northern hemisphere, you notice, is much lower elevation and also has much less impact craters. Now, who can tell me a theory as to why there are less impact craters in the northern hemisphere than there are in the southern hemisphere? You notice all the raised area of Mars is very much impacted, but the area in the northern hemisphere doesn't have as many impacts. It's all one impact crater. Hellas Planitia probably is one impact crater, but then there are multiple afterwards. So a giant impactor may have impacted the northern hemisphere. Okay. Earlier oceans. So if there were oceans covering the northern hemisphere, then there would be less impacts. Okay. So ancient oceans would have been in the lower elevations, and so the northern hemisphere would have been where most of the earlier oceans would have been, shallow seas. Okay. Also, with oceans, there would be newer sediment deposited into those oceans from water that flew off from the land. And so the idea is that the southern hemisphere, the surface of the southern hemisphere is much older than the surface on the northern hemisphere. Now, this is just from visual observation. They haven't done any actual age dating, which would be very useful to getting the actual dates rather than just relative dates of events. Okay. Now, Curiosity, you see, is located at a transition zone. So Curiosity is located at a transition zone. Why is that important, that it's located at a transition zone? So you see it's at an elevation transition. Where would that be if that was on Earth? What would we call that? What would we call that transition? Sea level? A beach. Very good. So Curiosity might be near the ocean sea level, okay? Yeah, it's a little above the equator. It's actually fairly close, a little bit above the equator. Actually, no, it's a little bit south of the equator, okay? So that would be in a transition of water, okay? Alrighty, let's move on here. Boy, my browse button keeps clicking off. Okay, so we were very lucky. So they had timed the Mars Reconnaissance Orbiter, as well as the Global Surveyor, as well as the Odyssey spacecraft, and the Express spacecraft from the European Space Agency, so that they all converged over. And this is quite a lot of mathematics. They all converged. They were all in the same area when Curiosity came down through. And this picture was taken of the parachute and Curiosity landing, coming down through the atmosphere. It was taken by the Mars Reconnaissance Orbiter. And the other satellites were used as communication. So they had very good communication right from the start of the mission. Okay, so Curiosity landed on October 5th, 2012. Okay, and here are some of the the mission goals of Curiosity. Okay, really to determine the planet's habitability. They were looking at did Mars have, or does it have now, an environment which is conducive to having some form of life. So they were analyzing the soil samples, drilling in the rocks, and also there's a couple of instruments that are looking at the climate. Okay, they're also looking, as they analyze the rocks, for chemical building blocks for life. Okay, now you see a web link down at the bottom, and this is about a 5-minute video, and some of you may have seen it. It's called the 7 Minutes of Terror. But if you would click on that right now, and Chantel, thank you for putting it in the chat box. Click on that, go to YouTube, and watch that video, and we'll come back and discuss it. Okay? So I'll give you about 5 minutes here, and I'll stop talking for a minute. Okay.
When people look at it, it looks crazy. That's a very natural thing. Sometimes when we look at it, it looks crazy. It is the result of reasoned engineering thought, but it still looks crazy. From the top of the atmosphere down to the surface, it takes us 7 minutes. It takes 14 minutes or so for the signal from the spacecraft to make it to Earth. That's how far Mars is away from us. So when we first get word that we've touched the top of the atmosphere, the vehicle has been alive or dead on the surface for at least 7 minutes.
Entry, descent, and landing, also known as EDL, is referred to as the 7 minutes of terror, because we've got literally 7 minutes to get from the top of the atmosphere to the surface of Mars, going from 13,000 miles an hour to 0 in perfect sequence, perfect choreography, perfect timing, and the computer has to do it all by itself with no help from the ground. If any one thing doesn't work just right, it's game over.
We slam into the atmosphere and develop so much aerodynamic drag. Our heat shield, it heats up and it glows like the surface of the sun. 1,600 degrees.
During entry, the vehicle is not only slowing down violently through the atmosphere, but also we are guiding it like an airplane to be able to land in a very narrow, constrained space. This is one of the biggest challenges that we're facing, and one that we had never attempted on Mars.
Mars is is actually really hard to slow down because it has just enough atmosphere that you have to deal with it. Otherwise, it will destroy your spacecraft. On the other hand, it doesn't have enough atmosphere to finish the job. We're still going about 1,000 miles an hour. So at that point, we use a parachute.
The parachute is the largest and strongest supersonic parachute that we've ever built to date. It has to be able to withstand 65,000 pounds of force, even though the parachute itself only weighs about 100 pounds.
When it opens up that fast, it's a neck-snapping 9 Gs.
At that point, we have to get that heat shield off. It's like a big lens cap blocking our view of the ground to the radar. The radar has to take just the right altitude and velocity measurements at just the right time, or the rest of the landing sequence won't work.
This big, huge parachute that we've got, it'll only slow us down to about 200 miles an hour. And that's not slow enough to land. So we have no choice, but we've got to cut it off and then come down in rockets. Once we turn those rocket motors on, if we don't do something, we're just going to smack right back into the parachute. So the first thing we do is make this really radical divert maneuver. We fly off to the side.
Diverting away from the parachute, killing our horizontal velocity and our vertical velocity, getting the rover moving straight up and down so it can look at the surface with its radar and see where we're going to land. And we head straight down to the bottom of a crater right beside a 6-kilometer high mountain.
We can't get those rocket engines too close to the ground, because if we were to descend propulsively with our engines all the way to the ground, we would essentially create this massive dust cloud. That dust cloud could then go and land on the rover. It could damage mechanisms and it could damage instruments. So the way we solve that problem is by using the sky crane maneuver.
20 meters above the surface, we have to lower the rover below us on a tether that's 21 feet long and then gently deposit it on its wheels on the surface.
As the rover touches down and is now on the ground, the descent stage is in a collision course with the rover. We must cut the bridle immediately and fly the descent stage to a safe distance from the rover.
Okay, is everyone done? Everyone was able to watch the video there? Yeah, I'm sure a lot of you have seen that before. That was one of the most shown videos during its time in that particular time, and it went viral. I don't know how many millions of views it had. So some of the data there. So the 7 minutes of terror. Who can explain why it was 7 minutes of terror? Why was the movie called 7 Minutes of Terror? Okay, there's radio blackout. Very good. Actually, it was just the gap between when things happened on Mars and the time that we knew about it on Earth. There was a 7-minute gap, so it took 7 minutes to get the information back to Earth. By the time they knew it had reached the atmosphere, it actually 7 minutes had already gone by and it was already on the surface. Okay, so it's a 14-minute travel time. All right, so by the time they knew it was on the surface, it had already. By the time they knew it was at the top of the atmosphere, it had been at the surface for 7 minutes. Okay. Yeah, the moon is about a second and a half. The light travel from the moon. Okay. So they had no control over it. You heard that. They had no control over it. Actually, any time during its mission. Well, they did fire retro rockets, but as it was going through the atmosphere, it was completely controlled by the computer. 13,000 miles per hour, just by aerodynamic braking down to 1,000 miles per hour. The parachute opened, that's the fastest that have ever tried to open a supersonic parachute. That actually was tested here at NASA Ames. You could Google the 80 by 120, 80 by 120, let me type that in, 80 by 120 wind tunnel. And that's where they tested the parachute for Curiosity. And the first couple of times that they tested it, it tore to shreds. It had a defect in it. Now this spacecraft cost $2.5 billion. That's with a B, $2.5 billion. So we definitely did not want it to not succeed. So that's how much there. Okay. Alrighty. Very good. But it was successful. It came down through, slowed down with vector rockets, and landed safely on the surface. A tremendous achievement of engineering. Now the target was the Gale crater, and this made it another challenge because they were landing inside of a huge crater, and with a mountain at the top, 5 kilometers high, so they couldn't be very far off to land, and they had a real narrow, I think it was 12 miles by 7 mile ellipse that they actually were aiming for. And part of the reason they were able to do that is because they had control rockets on the capsule as it came down through the atmosphere. So they actually, the computer was controlling where it was headed. Okay. And so if we compare the Gale crater to the Grand Canyon, the mountain in the Gale crater, the hill or the mountain in the Gale crater compares geologically to the Grand Canyon like this. And so this is 2 kilometers of sediments from top to bottom. Okay. Yeah, I'm not sure that it's not that steep, because Curiosity wouldn't be able to climb up if it's that steep. This is an exaggeration of elevation. Okay. Okay, so here's the landing ellipse, which was 12 miles by 7 miles, something like that. And they landed in one of those alluvial fans, not one of the ones we saw before, but this would be coming off the mountain there in the middle. And I forget the name of that mountain, but anyways, it was just on a previous slide. So this was a water channel that branched out into an alluvial fan down where Curiosity landed. And obviously, they wanted to go where the water was, and this would be a great place. Mount Sharp, very good, thank you, Vic. Mount Sharp. So the water flowed off of Mount Sharp, and they landed right at the bottom of this alluvial fan. So Curiosity has been traveling. It landed near the Bradbury landing site, named after Ray Bradbury, the science fiction author, and it is climbed along and climbed along and climbed along, and I think it's on somewhere around day Sol 300. Remember that every Earth day is about 2 Martian days, because it takes 687, well, oh no, an Earth day is only, no, every Martian day is about 20 minutes longer than an Earth day. Okay. And so Curiosity right now is headed towards the Yellowknife Bay, and so it's traveled quite a ways already. Okay. Yes, 37 minutes 22 seconds. Very good. Okay, excellent. I just remember that when the Mars scientists were working on the Mars mission, they had to come in 20 and 25 minutes later every day, and so pretty soon they were in the middle of the night. Okay, so right there at that alluvial fan, instantly we came across these sediments on the left and realized that this is very similar, obviously, to conglomerate here on Earth, and showed evidence that the rounded edges of the sediments were indicative of flowing water. So this was the first indication of flowing water on the surface. Okay. Here are some other images of tools that were used on Mars on the rover. The one on the left is the robotic arm. The wheels themselves unearth sediments to use, and then of course there's a scoop that can take up sediments and analyze them in a mass spectrometer, which is one of the instruments on the spacecraft. So this was the first Curiosity drill site, and you can see where the drill drilled there, and I've got a close-up of that next. And so the idea was that did they predict how long the water actually was there? Okay, they have predicted that it was probably a couple billion years ago that the water was there. They don't know how long it was there. I think that's probably going to have to come by actually doing age dating, by sending up, by doing radiocarbon dating, and Curiosity does not have that ability. Okay, so the idea to drill a borehole, we all know, I don't know if geologists, I'm a geologist, or took geology, I have a geology major in college. The surface of any rock is not really indicative of what the chemistry of the rock is, and so the idea is to drill down and get a sample from below the surface, which hasn't been changed by the surface. Okay. Now these cores are not more than a couple of inches. That's right. And so the reason that there's no water on the surface now is partly due to temperature, but also due to the low atmospheric pressure, which is about 1% of the atmospheric pressure here on Earth, and water, liquid water, is not stable at that atmospheric pressure. Thank you, Vic. Okay, so those are the boreholes. And then this is another indication of some close-up sediments that came out of the area where they scooped. On the right-hand side is after those have been sieved to a certain size. They sieved them and then put them into the analyzer to analyze them. Okay. So the sandy surface at rock nest, and then a scoop that was sieved. Okay. Geologists love this stuff. Okay, so those are mostly the areas on the surface. I'm going to do, you love it too, great Vic. So I'm going to go through a few slides here that are an activity, and that's what I do. I do K-12 education, and this is called the Mars Image Analysis Activity. This is primarily for middle school students, which would be about grades 6 through 9, something like that. I was an earth science teacher before coming to NASA 11 years ago, so I taught all this stuff, earth and space science, and so I love to be able to do it now. Okay, so the Mars Image Analysis. Oh, Shiva, you're a student. Fantastic. And hopefully you'll be around so I can tell where you're from. Or you can put in where you're from right now, but I want to kind of get a little bit of a not a bio, but some information. Oh, you're in Chicago. You may have been on some of my webinars before. The name sounds familiar. Okay. Shiva. Good. All right. Excellent. Are you a college student? I'm going to just run with it right now while you're there. Or what grade are you in, Shiva? I'm going to go to the next slide here. Okay, so the Mars Image Analysis activity is actually to help students and adults identify certain features on Mars. And down on the lower right you see, oh, 6th grade, okay, excellent. Okay, so the feature charts down on the lower right hand side give you a guide in order to identify features on a larger image, okay? And then the larger image is on the left, both taken in false light, and the two images on the larger image to the right, the two images that show the crater are a context image. In other words, the large image on the left was taken somewhere within the two context images there on the right in that larger images. Okay, so the sample themis image and the context images, and they have a little box, a little rectangle that shows where the working image was located. Okay, I think we come next to something more close up here. Oh, okay. We do also teach some relative age dating techniques. The one on the left is looking at craters, and no, the one on the left is looking at two age dating techniques. One is called the law of superposition, and principle of superposition, and the other one is called the principle of cross-cutting relationships. Okay, and then there are ways to relatively age date craters as well, depending on how much erosion has occurred and whether there have been other impacts or crosscuts across them. This is just relative age dating. This is not absolute dating. It's relative age dating. Okay. And so this is an image, and I don't know if you can see this or not, but this is having students work on scale. And so this image is an 18-kilometer swipe. Okay, all of these images in Mars images are the Mars image analysis, and you can download this. I'll show you how to do this later, this activity, if you're a teacher. Oh, she already put it up there. Very good. Okay, thank you, Chantel. So you can go to that site and look at the site and have these images and do these activities with your students. So then you, in order to produce a scale, you measure across the image in the classroom, and you get 21 centimeters. So tell me what the scale is going to be. If it's 18 kilometers, and you divide by 21 centimeters to find out how many kilometers per centimeter. So what's the ratio? You guys hopefully got a calculator on your computer. How many kilometers per centimeters? 21 centimeters across the image, and it's 18, represents 18 kilometers. So let's bring that up here. We'll go to the next slide so we don't have to take too much time on this. Okay, so there it is. I'm sorry. There it is. So 18 kilometers and 21 centimeters, okay? So who has done the math there? Okay, so 18 divided by 21 gives you how many kilometers per centimeter? It's not centimeter. No, you've probably done it backwards. So it's not 21 divided by 18. It's 18 divided by 21. We want kilometers per centimeter. All right. Come on, students. You got to do math in order to do science. Okay, 0.856. Very good. All right. You know that I use smarter than a sixth grader. Very good, Sheba. Okay. You showed up all the adults, and that's usually the case. So. Thank you so much for banging that out. Okay, 0.86. We rounded it off to 0.86. Okay, so who can tell me how wide in real life is the channel on the right? It's 2 centimeters. So who can tell me how wide that channel is on the right? So this is what you do with your students in the classroom: is you learn about scale and how to determine a scale factor, and then how to apply that to the images. Okay. A little over a mile. Okay. All right. Is that a scientific answer? Well, let's see. To be exact, well, that's what you have to do for the math. We'll keep you in suspense a little bit more. Sheba's going to come up with the answer. I got 1.72. So what you do is take 0.87 and multiply by 2. Okay? So it should be 0.86 times 2 should be about 1.72. Okay? A mile is 1.6 kilometers. Very good. So you're right. Okay, very good. A little bit over a mile. Very good. Excellent. Yeah, conversions. There you go. Bad at math as usual. Okay. Okay, so this is in kilometers. Excellent. Excellent. Leo, you were correct all along there. All right, excellent. Okay, so that is our student activity. And let's see what else we've got here. Okay, there's also activities for younger students. So you can take objects that you have maybe in the classroom, like a pencil eraser or pennies or small Post-its, and you can compare those to the actual size and relationship on the images. Okay, so you can talk a little bit about the relative sizes. Now, if you're looking for the older students in high school, you can calculate some other things. If you know the angle of incidence, the angle that the sun is coming in towards the surface, then you can actually determine the depth of certain objects or the height of certain raised objects like a mountain or a cliff. Okay, so say we have a cliff that is 0.86 kilometers wide, okay, and we can use trigonometry because the tangent equals the opposite over the hypotenuse, okay, and so if we take the opposite leg, which is 0.86, and you can do the math there and divide the opposite leg by the tangent of the angle, and you can figure out how deep this is. Okay? Oh, it's not opposite over, adjacent over, tangent equals adjacent over opposite. No, adjacent over hypotenuse, tangent, TOA. Adjacent over hypotenuse. Sorry about that. T-A-O. Very good. Opposite over adjacent. Okay. The tangent of the angle equals opposite. Okay. Very good. Sorry about that. It's been a long time. Yeah, T-O-A, TOA. Very good. And S-O-H, right? Opposite over hypotenuse is sine, and then cosine is... Okay, sorry about that. It's been a long time since I took trig. Very good. Excellent. Okay, so you end up with 0.14. I got to brush up on my trigonometry and calculus there. Thank you so much. Okay. So those are some of the things that you can do with this activity, and then you can look at different features and determine how they are formed, and then do a measurement on them and use the relative age dating techniques, and then you give the evidence for how you came up with the relative ages of different features. Okay, so this is kind of the student log as you look at different features. Okay. Very good. So this would be the data collection. You'd take a feature, determine what may have caused that feature, what may have created that feature, whether it would be water, wind, volcanic, cratering, or canyons, and then do measurements on it. Okay? All right. So that about wraps it up. I didn't know if I would go more than an hour, but it turns out it was right on the button, 1 hour. Again, here's my email address, and I will type this in. Now hang out just for a second, guys, because I would love to go down person by person real quickly and have you give me a couple of pieces of information for me to use on my report. Okay, I'm typing in my NASA email address in case you want to email me. Click on that, and you can email me in order to get a copy of this PowerPoint. Now again, this is it's open source property, but it's used for education. Okay, Danelle, you're first up. Tell me the country and whether you're a student, teacher, or just what your profession is. And what grade level, if you teach, what grade level. Okay? Retired professor. Excellent. Okay. USA, retired community college. Excellent. So we have one CC community college. Okay, excellent. And Chantel, you're You're a mom, right? Any other things going on there? Okay, and Vic, you said you told me before. Oh, you've been to NASA, but what's your profession now? Computer systems. Okay, computer information systems. Very good. Okay, and Leo. Leo is retired aerospace engineer. You were my backup there. Okay, excellent. So you're close to NASA Ames here. Okay, Nate, Nature. Oh, Vic's gonna Texas retired. Okay, Vic is in Texas. Okay, you're in the UK, and what do you do for work, Nat? BBC, retired BBC. Okay, very cool. Alrighty. And Sheba, I already know that you're in 6th grade and the smartest person in the science circle, so thank you so much. You're from Chicago, 6th grader. Okay. You know we have a show called Are You Smarter Than a 5th Grader? And 6th grader's even tougher. So how about Phil? Where are you from, Phil? Phil is Italy, IT program manager. Okay. Very cool. Italy. Excellent. Is in IT. Excellent. Cool. Let's see. Who else we got here? Leo, did you already chime in? Leo, Nate, Vic, Leo, Danelle. Yeah, anybody can just go ahead and put this in. Meriden. Curriculum and game developer. Okay. Excellent. In Carolina. Carolina. Very good. Okay, curriculum and game development. Excellent. Well, I hope you enjoyed this curriculum development. Okay. Let's see. And I guess that's everyone. I did a gig for NASA a couple of years ago, but the program sort of disappeared. Virtual magnet. Okay. I haven't heard that one. Haven't heard of that one. Okay, well, definitely. Any questions? Sounds like this was a fairly knowledgeable group here. Trying to get some youngsters hooked on science. That's cool. That is so cool. Did I hear from Hades? Yeah, I did, I guess. I'm going back here and seeing if I heard from Hades. Yeah. Hades. Okay. Thanks to both Tony and Chantel for organizing this. Yeah, great. Well, I'm glad you were all able to join us. Depth. Did I hear from you, Depth? Does it look like Depth? It's written in a different language there. Okay, Mariad, thank you so much. I appreciate that. All right, Vic, thank you. Thanks for the help earlier on as well. Okay, guys, well, you have a great day. I'll hang out for a minute here to see if there's any more questions. Okay, how many levels of surprises is AI on a mission like Curiosity planned for? How many levels of surprises? You know, there's not. I don't think there's a lot of AI unless it's Doppler on Curiosity. We haven't heard that there are instruments on there for AI, but certainly we would welcome having some artificial intelligence, or having some intelligence there. Yes, I think European Space Agency and the U.S. Space Agency is looking towards the 2020s for joint rover missions on Mars. Okay. Okay. What do you think about the commercial missions around Mars and the one-way colonists? You know, there's not a lot of credibility given to the one-way mission to Mars. A lot of people have signed up for that. It's called One Mars, and I talked to the scientists here at NASA Ames who are Mars scientists who are, you know, serious about possibly going and exploring the surface of Mars. It is a ways off still. I don't think the One Mars has got sponsors in order to do what it wants to do. It's fairly grassroots, I guess you'd call it. The commercial space endeavors like SpaceX, I think that they're a more serious opportunity to eventually get people to Mars. Elon Musk is quite a driven person, obviously, with Tesla and with SpaceX, and he's got another business going now. So I think that his group may end up being the first people, but we'll see. We'll see if you know, NASA and its collaborators get the manned space program going again. How can a young person start interning with space-related science work? Well, if you're in high school, they used to have internships through high school. Now those are mostly as an undergrad, but you can go and get involved at the NASA website. There are webcasts you can join. NASA Facebook. There's also a group on NASA. If you go to the NASA website, you can find that. So I would definitely be involved online as much as possible. And also, sometimes high school students get to come and do internships. It's mostly people who are kids of the scientists who are here. So there used to be a much larger program called the Inspire program, which has gone away due to budget constraints. Okay? Anybody else? I've had a lot of fun doing this. I really appreciate it. Do you know other Second Life NASA reps? You know, because the collab, which is on STEM Island here, was run out of NASA Ames, and that was shut down apparently quite a while ago. I don't know other colleagues who are on Second Life or would be willing to present. I can ask around. I know people are very busy and all right, great. Well, I look forward to coming back and giving some other presentations here. It was great fun. Is there anyone who hasn't checked in with me? I think I have 8 people down for their like little mini bios, and I haven't heard from maybe a couple of you because there were 11 people, I think. So let's see. Hades, did I get your location? I can't. You tell me your location. No, I don't have Hades. Where are you calling in from, Hades? And what's your profession, if you don't mind sharing? Belgium. Okay, fantastic. And why were you interested in coming in and viewing this? Scientist, teacher, just interested citizen? Okay, and then the one that spelled with, oh, okay, I'll contact you later about Mars settlement game we developed for middle and high schools. That would be cool. Well, you've got my email address, and hopefully you can get back to me with that. Okay? The other person who I didn't hear from, I don't think, is the APETH, or APETN, which is Greek to me. Timing was wrong in Japan. Yeah, Yeah, I can understand that. We can work on Arette, okay? Arette, hi Arette. And where are you calling in from, Arette? Irene. Finland. Very good. Excellent, excellent. What do you do in Finland? Is it Irene? Irene. Anyway, I'm glad you joined us, and thank you for sharing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Cool. Excellent. Well, I really appreciate you coming in. Topo, were you here for the talk? Did you see most of it, or did you just sneak in at the end? You and Q. Anyway, I hope that worked out fine for all of you. I had a great time, and thank you so much. I'm gonna sign off. I actually have another telecon today to connect with. So, alrighty. So thank you so much for joining us. Okay, Chantel, we'll talk sometime soon. You guys all take care. What's that?
That was very interesting. I heard part of your stuff. How did it go? No, Second Life, right?
Yeah, I'm going to go ahead.
Still is.